Okay, so this is the last module of the practical machine learning course, lecture 5. And it is actually in this course, I'm going to talk about some of the advanced machine learning model. Okay, so here is the outline of this module. So first we'll give a quick overview of the machine learning model, and then we will discuss about generative model, and then we will spend some time talking about representation learning. And then I will talk about how to optimize neural network model. And lastly, I will give the summary of the course. Okay, so I have shown this plots on the very first day of our class. And I just want to show it again to give you a refresher about what's happening here. We have mainly been talking about the machine learning with labeled data, which is, for example, classification or regression. But actually, machine learning is not restricted to only labeled data. So if you look at this axis, I draw a continuous axis from labeled to unlabeled, from completely labeled data to completely no labeled data. And actually among there, we can take several different data points. For example, you can have a label that does not arrive on time when you are training the neural network. To deal with that, we can do reinforcement learning. You can have data with both, you can have both labeled and unlabeled data. And to deal with that, you can do a semi-supervised learning. So your data might have very little label data in it. So in this case, you can do what we call the few shot learning. And even if you completely have no label of your data, you can still do this contrastive representation learning, which actually turns out to be very effective. And also we discussed about the generative model, which we can use to generate fake images or fake waveforms. And also there are some other tasks like pattern recognition or meta learning. Okay, so let's start with talking about the generative model. So what is a generative model? So the idea is to generate fake images, which is indistinguishable from a real image that we see. So this is an unsupervised learning approach, meaning that it does not need a label on top of it. And actually on the right, you can see that there are several generated images of the bedroom, and actually neither of them exist in the real world. They are all fake images. So how does this generative model work? So we can actually formulate it using the Bayes rules. So this is a famous Bayes rules where we have the posterior equals to prior times the likelihood function divided by the Bayes evidence. So basically in a generative model, you have Z, which you can consider as a randomly sampled generating seed. And this Z would follow some kind of a prior distribution PZ. And you also have this function PZ given X. So this is the likelihood function in Bayes rule. And this is also the function you would like to fit. You would like to fit when you are doing the generative model. So neural network model try to approximate this likelihood function in order to produce image from arbitrary input Z. So that's how it works. So before we start talking about actual generative model, I will start with a convolutional autoencoder model. So basically, what a convolutional autoencoder does is that it concatenates two convolutional neural networks back to back. So there is an encoder part, which is a stack of convolutional layer, so this encoder part encodes each image into a feature vector of given length. And then the decoder part is a stack of deconvolutional layer, which decode the same image from this feature vector space back to the original image. So what happens in the convolutional autoencoder is that it's trained to reconstruct the input image from the latent space vector. So when we train it, as I mentioned earlier, we are minimizing the mean square error loss between the input images and the reconstructed images. So in this case, each image is encoded into the latent space vector by the encoder, and it can be reconstructed by the decoder. So the first generative model we will introduce is called variational autoencoder. So the idea is that we can modify convolutional autoencoder to generate fake images. using its decoder part. So in convolutional autoencoder, the latent space vector contains all information you need to reconstruct the image. But unfortunately, it does not follow any particular distribution. Like its first value can be between 0 to 1, its second value can be between 1,000 to 2,000. You really don't know what the range of those values are and what kind of distribution they will follow. Therefore, a valid value for generating a reasonable image to fall in any range, and it's very hard to somewhat reproduce it. So the idea of variational autoencoder add another loss to regulate the latent space vector. And this loss is what we call a KL divergence loss. So a KL divergence loss basically measures the distance between two probability distributions. So what we want to do is that we want to train to regulate this latent space vector, which has the amount of, well, the number of dimensions we define. For example, it can be 3-dimensional, 192-dimensional. We want to train this latent space vector to follow a multi-dimensional Gaussian distribution. So basically, in a variational autoencoder, you have two loss. One is the original mean square error loss, which makes sure that the reconstructed image will reproduce the input image. And on the other hand, you have the KL divergence loss, which regulates the latent space representation to be a multidimensional Gaussian. So yeah, as I talked about on the last slide, so MSE loss makes sure that the generated image and input image are similar, while the KL divergence loss makes sure that the latent space would follow a multidimensional Gaussian distribution. So whenever you would like to generate a fake image, what you can do is that you can sample a value from this multidimensional Gaussian space. So you know that value will be valid because during training, you are training your latent space to reproduce the shape of the multidimensional Gaussian. And then you can just directly feed this value into your decoder, and your decoder will produce your fake image. So this is how variational autoencoder works. The other generative model we'll be talking about is the generative adversarial network, which is pretty famous. It's known as a GAN network. So GAN actually generated images using a different approach. So GAN has two parts. The first part is called a generator. So generator exhibits the same structure as a decoder of the convolutional autoencoder and variational autoencoder. Basically, it's a stack of deconvolutional layer, and it produces fake images based on the input of a random noise. So before training, a fake image being produced by the generator will just also be a random noise because the parameters are just all random parameters. And the GAN also has a part called discriminator. It's basically a very typical binary neural network classifier. Its goal is to classify whether the input image is real or fake. So when training the GAN, we use unlabeled real image. So GAN is unsupervised learning. It does not require any label of the image. For each real image, the generator will generate a fake image from random noise. So the goal of the generator is to try to fool the discriminator with a generated fake image. And the goal of the discriminator is to try to classify whether the fake image is real or not. So when you feed the image to the discriminator, you actually feed in each of your image and also the fake image generated by the generator. And here you also have an adversarial loss, which is written in this form. So the training goal is a generated fake image can no longer be distinguished from the real image. So that's why we call it an adversarial network, because the generator and discriminator is doing like an adversarial training against each other. Okay, so we will try to compare variational autoencoder and GAN. So this two model looks very different, but they achieve similar goals, which is to generate fake image. So which one of them is better? Variational autoencoder explicitly regulates the likelihood function through the KL divergence loss. So I require the likelihood function to be a multidimensional Gaussian. So this actually isn't a very good approach because you never know what the actual likelihood function is supposed to look like. It may never be able to be, moved, be kind of transferred from a multidimensional Gaussian to the actual likelihood function. On the other hand, the generative adversarial network GAN actually does not make any assumption on the likelihood function. The likelihood function is produced through the generator and then compared to the real image by the discriminator. So this gives the model more freedom to fit a proper likelihood function instead of trying to force it to be a multidimensional Gaussian. So that's why in general, GAN is a better generative model approach compared to a vanilla variational autoencoder model. Okay, so the other model I'm planning to talk about is a semi-supervised learning with GAN. So suppose we have data sets. So remember what I said, semi-supervised learning is a learning scheme where we have both labeled and unlabeled data. So suppose we have data set with both labeled and unlabeled data. So we want both type of data to jointly contribute to our training task. So in this way, what we can do is that we can utilize the GAN network to perform a semi-supervised learning. So basically, if we have unlabeled data, we can ask the discriminator to classify whether the image is real or fake only. But if you have data that's labeled, we can ask the discriminator to classify whether the image is real or fake, and also the class of the actual inputs. For example, if we are doing like an animal generation or classification, we can ask it to say, like, is the animal cat, is the animal dog, etc. So in this way, when during training, you are actually using both the labeled and unlabeled data. And the unlabeled data will help you discriminating. Well, this is actually reversed. So, so the idea that unlabeled data will also help the discriminator to discriminate, while the labeled data will also help the generator for the generation purpose. Okay, this is the first module we have. Is there any questions?
So is this in this generative adversarial network, it's like the hidden state distribution are predefined, right?
Sorry, pardon?
So the hidden state distributions are predefined in this generative adversarial network.
Well, actually, in GAN, there's no latent states, because basically, when we are talking about latent state in a autoencoder model, it's encoded from the image. But in GAN, we are not encoding anything from the image, right? We're just started from random noise, and then using a random noise to generate a fake image. So there is actually no latent state in GAN.
All right. Yeah. Okay. Thank you.
Okay, great. We'll take a 1 minute break and then go to the next module. Okay, great. We'll keep going then. So in the second module of this course, I would like to talk about representation learning. So on the second module, we discussed about this convolutional neural network. And we say it actually has two parts. One is a feature extraction. The other one is a classification part. So what the feature extraction, so the feature extraction, So basically, every single neural network classifier kind of follows this structure, which, for example, if when we are talking about recurrent neural network, our feature extractor will be the RNN layer or the multi-head self-attention layer we discussed in the model 3 and 4. And the classifier part is basically just a stacks of fully connected neural network. So the goal of the feature extractor is to convert each input image or waveform into a specific representation of the image or the waveform. So in the case of the convolutional neural network classifier, what happened here is that I convert this 50 times 25 times 34 dimensional images into a 198 dimensional vector. So this is a representation of this input image. So this representation is then fed to the classifier, which is a stack of fully connected neural network for the classification decision. So it turns out that learning just the representation instead of the final classification decision is actually extremely useful. So the learned representation will contain important feature of the data to actually perform the classification. This representation can then be transferred to different tasks. And even better, learning a representation oftentimes does not require labels. So this is a very big advantage because labeling data is an expensive process. And in the real world, labeled data are actually hard to acquire compared to unlabeled data. I mean, I think that's also what we see in like a neutrino experiment. And because the representation learning can be conducted in a contrastive self-supervised way. So we will discuss about this later. We will first start with transfer learning, which is how we can utilize the learned representation to help our task. So the idea of transfer learning is that what has been learned in one setting is exploited to improve generalization in another setting. So when I talk about setting, I usually means both the data we are trying to deal with and the task we're trying to perform. In transfer learning, we usually talk about two terms. One is called source domain, where, for example, we have a lot of data and would like to train our machine on, and also a target domain where we have limited data, but we would like the machine to perform well on. So when you first see these two concepts, it might be confusing with the idea we talk about where we have a training set and a validation set. So that's actually different. So remember, the training set and validation set, they are from exactly the same data set. They are just they're just split randomly so that we only train on part of the data and try to generalize to the other part of the data. So in transfer learning, the source domain and target domain doesn't have to come to the same type of data set. It doesn't have to come from the same data set. So the source and target domain can be different, but they are correlated. So in this case, the representation is more useful than the classification decision because it contains more information. So there are two types of transfer learning. The first type is called transducive transfer learning, and it's also sometimes called domain adaptation. So the idea is that when you have the same task, for example, you are trying to classify, but you have different data in the same feature space. So for example, if I'm trying to classify Pokemon, I can actually pull out the feature extractor from ImageNet. So ImageNet is a very large neural network trained by Google. It is trained by millions and billions of images. And then what I can do is I can hook this feature extractor to a new classifier. By classifier, I mean a series of fully connected neural network on top. So although ImageNet may not be trained on Pokemon, it may have never seen Pokemon before, but because it's trained on a lot of images, it's still very good at capturing the tone, the hue, the edge of each of the image. So if you use the ImageNet feature extractor to classify Pokemon, it's still going to be very efficient in terms of fulfilling the task. So the other type of transfer learning is called inductive transfer learning. So the idea is that to perform it on the same data, but on a different task. So a very simple example, for example, if you want to train a generative adversarial neural network to generate cat or dog, what I can do is that I can pre-train a classifier which classifies cat and dog. And then I use that as a discriminator part of the GAN network. So as we just discussed a bit earlier. Okay, so given that learning the representation is very useful, then how can we actually learn the representation? And even better, how can we learn the representation without the label of the data? So in order to talk about this, we will have to go through the concept of contrastive self-supervised learning. So I would like to start to talk about this using a psychological experiment. So so this is actually an experiment of asking people to draw a $1 dollar bill with and without the dollar bill present. So if you ask someone to draw the $1 dollar bill with the dollar bill in front of you, then you can see you capture all the fine details. You capture the $1, you capture the George Washington, you capture all the letters, all the numbers, and you capture all the patterns on top of the dollar bill. But if you ask the same person to draw the dollar bill without the bill present, then what you only see is that you only capture only capture a small number of important features of the dollar bill, which is, for example, the one on the corner, which indicates how much it is, and also the George Washington as the center, and also the "In God We Trust" sentence. So this actually reveals the fact that when we human beings are learning, we do not learn all the gory details of the objects, but only the feature that makes the object outstanding or contrastive with a similar object. So in case of the dollar bill, we only learn the part which makes a $1 bill different from a $10 or $100. So this is the constitution of the idea of contrastive self-supervised learning. So basically, when you have a generative model, you have your input data, you feed it into some fancy neural network model, and you get another type of data. So, and the loss is measured in the output data X1 space. For example, you can do autoencoders and some other algorithm. So, but on the contrastive learning side, what happens is that you have two data points, X1 and X0, and you feed both of them into your neural network, and you want the neural network to classify whether they are similar or not. So in this case, the loss is actually measured in the representation space. So some of the possible models are TCN, CPC, and DeepInfoMax. So we will actually talk about DeepInfoMax today, which I think is a very interesting and useful algorithm. So the idea of learning the representation is that we want to learn an embedding or the representation of each data so that similar data points are closer and dissimilar data points are further away. So this does not require any label data. So that's actually a huge advantage of representation learning and contrastive self-supervised learning compared to other supervised labeled learning scheme. And actually, it has been observed that the performance of contrastive self-supervised learning has surpassed traditional supervised learning approach, for example, AlexNet. Using a few, and after training this representation, what we can do is that we can use a few anchors to regulate the representation space to allow it to achieve our goals. Okay, so we will discuss one of the contrastive self-supervised learning model, which is called DeepInfoMax. So the idea is not too complicated, and this is the original paper. So let me first redefine some of the concepts. So when we pull out this feature extractor from the convolutional neural network, we have a series of feature maps. So this feature map is what we call the low-level feature map. You can see it got extracted right after the input image of the CNN. And then after stacking several CNNs on top of each other, and eventually this converts this feature map into a feature vector, into a 192 dimensional feature vector at the very end. So the idea of the deep informatics is to utilize both the high-level feature vector and the low-level feature map. And it passed both of them to a neural network to discriminate to a discriminator to get a score. So we call the classification decision real if the feature vector and the feature map are from the same image. And what we can do is that we can also replace the feature map of this image with another image, and then we pass it to the discriminator, and then this discriminator, we define this as a fake image because now the feature map and the feature vector are not from the same image. So this discriminator is actually a way of quoting what we call the mutual information. So mutual information measures the mutual dependence of the two variables. So the idea of deep informatics is that if the lower level feature map and higher level feature vector are from the same image, then their mutual information should be high, meaning that they are highly dependent. If the feature map and feature vector are not from the same image, then their mutual information should be low, which means they are mutually independent. That's why they have a low mutual information. So deep informatics actually has I think it has a pretty good analogy with the attention mechanism that we talked about 2 modules ago. So in the attention mechanism, we discussed that in a waveform like this, if a hidden state H3 is important, then when we calculating the attention score is going to be high because the information from H3 got preserved until the last hidden state output. So deep informatics is kind of the same logic. So remember, feature vector is actually quoted after each level, each feature map, after the low level feature map. So if the feature vector accurately represents the image, then its mutual information with a real low level feature map should be high, meaning that they are highly dependent, just like the attention score of the attention mechanism will be high. So if the feature vector does not accurately, and at the same time is mutual information with a fake low-level feature map, because remember the fake low-level feature map actually comes from a different image. So that's is the mutual information will be low in that case. So deep informatics does not directly produce you a classification decision, but it gives you this feature vector after training, which can be used as a representation to facilitate other tasks. For example, if you want to build a classifier on top of it, you can just hook another classification neural network on this feature vector. And this will allow you to very easily train the new classifier. Okay, great. So this is a second section where we talk about transfer learning. Are there any questions? So Wenchen, I see you raise your hand.
Yeah, good timing. Actually, can you talk more about the score of real and fake? I'm a little bit lost how they are exactly determined.
Oh, sure. 1 second. Yeah, so basically what happened is, so you did get this part where I talk about the low level feature map and high level feature vector, right?
I heard you, but I'm not sure I completely understand. What same image and different image, but why I think about the training, I always thought of, I always think about them as an ensemble of images, right? That's always what you need, a series of images. Do you mean coming from the same catalog, or do you mean exactly the same image?
No, actually not. So it does mean the same image here. So remember when we talk about the idea of a contrastive learning, you are feeding in 2 data points and you are measuring whether they are similar or not. So the idea is that if the 2 images are exactly the same image, then their similarity will be maximum, right? They will be most similar. If the 2 images are from different images, then their similarity will reduce. So the idea of this score, so well, you can call it a score or you can call it the mutual information. And well, I don't really want to give a very rigorous definition of mutual information here, but you can think of it as some kind of correlation. So the idea is that you want the feature map to be correlated to your feature vector. So when you are using, so basically when you pass an image through your CNN feature extractor, which is the convolutional part of the CNN classifier, you will produce a feature map at the very beginning. So for example, after your first convolutional layer, you get a feature map here. And then after several convolutional layers, eventually you will have a feature vector. So
yes.
yeah, so if the feature map and the feature vector are from the same image, then their mutual information or their correlation should be very high. So if the feature map,
how can they not be from the same image? I mean, you are feeding one image in this particular case.
well, basically the way is to feed in two images, right? So
okay, so
yeah.
you are feeding, okay. But then I actually see three cases, like, you know, the two images are identical. The two images are both cats, but and the third scenario is one image is a cat, another image is a car. I mean, what in the case where you feed two images of both are cats, do you get a score of real or do you get a score of fake?
Okay, so Wenqing, I think what you are thinking is still in terms of the supervised learning where we have label for each image. So here we don't have any label. So we don't know what the image is. This is a domain of supervised learning.
Okay,
yeah.
But do you have the case where you have cat images mixed with cat images?
Sure, that's possible. So, but in that case, we only have two possibilities, which is that whether the two images are the same or whether the two images are different, because we don't know what they are. We don't have a label.
So even if those two images are both of cats, they will be considered to be different images and therefore fake.
Yes. Well, yes, they are training toward fake. But if you have, for example, if you have cat and car in your image pool, then after a trained deep info max, if the two cats are exactly the same, they are exactly the same cat, then it's gonna be a real image. And if, for example, one cat is a blue cat, one cat is a white cat, then they are different images. Yes. So when training, you will try to draw it toward the fake end.
Okay, now I begin. Yeah. Okay, so in other words, this real to fake is a scale. It's not necessarily
exactly.
You know, 0 and 1. It's not binary. It's not binary.
Yeah, exactly. Yes. So
okay, now I understand much better. Okay, thank you.
Yeah. So actually, I just want to add, I think Wenqing brings up a very good point. So basically, the training, the effect of the training is that, well, let's stick with the previous example where we have a white cat and a blue cat. So let's say your primary feature map and feature vector come from the blue cat, and then you replace it with a white cat. So in that case, it's a fake image. So the neural network is going to try to pull it to the fake. But the neural network has also seen that if you replace, for example, if you replace the feature map of the blue cat with a car, so a car is much more different from a cat. So it's going to be more fake than the white cat case. So in this case, the training is actually going to push the blue cat and white cat to be like more similar, while leaving the car to be far different from the rest of the waveform. So this is how it works. Okay, great. Are there any other questions? Okay, if not, let's take a 1 minute break and we will continue to the last some more. Okay, so in the last module, we will discuss about how to tune a neural network. So I just want to compare something we are very familiar with, which is likelihood fit, to something that we are probably not that familiar, which is how to tune a machine learning model. So a likelihood fit is basically what you do is that you fit the Monte Carlo energy spectrum to data. And you have the fit is actually guided by a very well-defined likelihood function. We know we already use the bin likelihood for a neutrino experiment. And the evaluation of each step of the likelihood function is very cheap. So you basically take a few microseconds or even less to perform the computation. And it requires a lot of evaluation, and the result is usually quite accurate. So you generally is not a big problem to find the global maximum, global minimum of your optimization. So for example, in the frequent test approach, you do the gradient descent fit using min-v, and in the Bayesian case, you do the Markov chain Monte Carlo or Hamiltonian Monte Carlo fit. Model tuning is actually a completely different problem, although they both are kind of falling under the category of optimization. So the idea is to change the hyperparameter of the model to achieve best performance. And I will give a definition of hyperparameter in the next slide. There is not a well-defined likelihood function like what we did in the likelihood fit. So this is considered as a black box optimization problem. The evaluation of each step is usually very, very expensive. Like what we do is that we define a new network, we train it, and then we evaluate it on certain kind of for example, rejection efficiency metric. So this training of neural network could take hours to days. So it's extremely expensive. So that's why the model tuning task is usually a search instead of a fit. So by fit, I mean I would like the algorithm to get to the local minimum accurately within some kind of uncertainty. But the idea of search is that I want the algorithm to run for a few steps. And in a given finite steps, I would like to explore more parameter space while exploit the best model hyperparameter. So the longer I run it, the better performance I would get. But I will never claim that I will, by doing this model tuning, I will get to the best model in the world to achieve this task. So basically, the efficiency of model tuning scales with your computational power, scale with the number of steps you search. What we are searching for. So what are we actually searching for in a neural network model? So in neural network model, there are two types of parameters. One type is what we call the kernel parameter, or sometimes also called trainable parameters. So for example, the parameters you store in the convolutional kernel, which is a square filter you slide through the surface of the image, all the parameters stored in the recurrent neural network. So those are the parameters that changes during the training. So that's definitely not the parameter we're trying to search. The other type of parameters are called hyperparameters. So those are the parameters that define the structure of the network, and thus they remain unchanged during the training. For example, what's your batch size of the mini batch? How many layers your neural network have? How many channels in your convolutional neural network? How many neurons per channel, etc. Those parameters never change during your training process. And that's why they are called the hyperparameter. So some hyperparameters are correlated or anti-correlated. For example, the learning rate and the regularization strength parameter, for example, the dropout rate, usually they have some kind of anti-correlation. So each time we change the hyperparameter, we are pretty much creating a new model. And then the new model is trained and evaluated on the same data set to perform the hyperparameter search. And lastly, we want to quote some kind of metric, one metric to compare the performance. For example, the final loss, the accuracy of the model, or the area on the curve or the ROC curve, etc. So how do we tune our model? There is an ancient art which is called graduate student descent. So the idea that you first build your model and then you ask your graduate student to figure out the best parameters. The pros of this model is that it's human intelligence based. But the cons is that you need to have a graduate student. You need to hire a graduate student as a PI. So it's not really too valid for postdoc like me. So the other way we can do is a grid search. So this is a pretty, I think this is a pretty popular technique. So the pros of a grid search is that it always gives the best performance if your grid is fine enough. But the con is that is the most expensive method, and it also suffers heavily from the curse of dimensionality. So the idea of curse of dimensionality is that the space you need to search grows grows very quickly as you increase the dimension. So if you're only doing like a one-dimensional search, then it's very easy to do a grid search. But if you do two-dimension, like for example, if you do one-dimensional search, you only need 3 points. But if you do two-dimension, you need 9 points. And if you want to do three-dimensional, you have like 27 points. So the number of points you need to evaluate grows very fastly. Even worse, generally, when we train a machine learning model, we are not just searching for one dimension, we're searching for many dimensions. The other approach is a random search approach. So random search approach is less expensive than grid search. And it actually suits better for the machine learning model since some of the parameters are unimportant parameters. So for example, if you look at this case, so the blue region represents the actual likelihood value. So you can see for unimportant parameters, the grid search is spending a lot of points on these unimportant parameters. For example, these three are with the same, they have the same important parameter, but they are just varying on the unimportant parameters. So these three are pretty much waste, because it really only search like once on these important parameters. So, but if you have random search, then you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So all the 9 points kind of contribute to this important parameter. So that's why a random search actually performs better than grid search on a machine learning model. So the cons is that it does not utilize a correlation between parameters that we talked about on last slide, and it also suffers less from the curse of dimensionality, but for large parameter space, you still need to sample a lot of points. And that's actually also a kind of a waste. So with the same number of evaluations, random search is better than grid search for machine learning model. So the model I would like to talk about today is actually called Gaussian process. It's actually called Bayesian optimization, and it utilizes a statistical concept called Gaussian process. So a Bayesian optimization would perform better than simple random search by incorporating the parameter correlations, because it assumes the input is proper. That means if your input change by a little bit, your model's performance will also change a little bit. So what is a Gaussian process? A Gaussian process is a Gaussian where the mean and the variance are both functions. So you can also think of a 1D Gaussian process as a finite dimensional multivariate Gaussian. So the idea of Bayesian optimization is that start with the Gaussian process prior on the hyperparameter of the model. And the input, so the input to the Gaussian process is the possible values of all the hyperparameters. So each time we make an evaluation, we are evaluating at point of the Gaussian process. When we do the evaluation, we can see the uncertainty of the Gaussian process, the span got decreased to 0. So because we know exactly the value at this point. And then we construct the acquisition function after each step. And this acquisition function will pick the highest value as the next step of improvements. So basically it's a Bayesian process because each step is based on all the previous steps. So there are actually, this kind of search actually exhibit the explore versus exploit nature. So the idea of explore is to evaluate a region with maximum uncertainty. Actually, well, how do I'm trying to stop. So for example, if I want to explore, I would explore here because this region has a maximum uncertainty and I don't know it very well. But if I want to exploit, it means evaluate the region that has the highest probability to make an improvement. For example, if I want to exploit, I would exploit here because I can see this has some maximum possible upper confidence band. So basically in Bayesian optimization, we already perform a pre-run with a few randomly sampled trials. And then we run the Bayesian optimization to explore or exploit. Since we do not have any information about the model before we pre-run, we basically just sample uniformly as possible. So to sample uniformly in a high dimensional probability space, we use the Sobel sequence. It's a sequential sampling technique to sample from a high dimensional space and the sample points are more uniform than random sampling. So you can see on top is a sampling from a Sobol sequence, and on bottom is a sampling from a true, the pure pseudo-random sampler. So in this case, we can actually explore the parameter space in a pseudo-grid search manner, but with finite points. So the Bayesian optimization will be conducted according to the acquisition function after we initialize our pre-run with the field points. So why is Bayesian optimization better? So Bayesian optimization uses the parameter correlation to avoid redundant evaluation. So basically, by assuming the Bayesian nature, the Gaussian process nature of our parameter, we are assuming that each parameter is a multidimensional Gaussian which has some kind of correlation amount. So it will only so the acquisition function will force us to only search in the region that will most likely lead to a performance improvement, and thus is much less expensive than the grid search and random search. So for example, if you are searching this Gaussian process, your grid search or random search algorithm will still place points in this range, in this cyan range. But your Bayesian optimization will never check this range because it has seen that this range has a very low upper confidence span. It also has a very low values here. So it's highly unlikely that this point will make any improvement. Instead, it will actually put its strength on this part and this part where it has where it's most likely to give you an improvement on your searching result. So Bayesian optimization performs better as you introduce more evaluation steps. So this is ideal for model tuning problem as we discussed earlier, because we want our algorithm to scale with the strength of the search, of the number of the computational power. And Bayesian optimization also assume a Gaussian nature of the input hyperparameters, which is actually not too far away from the reality. So a final word about model tuning, that's I want to say that Bayesian optimization is also suitable for other expensive tuning tasks, for example, tuning a Monte Carlo simulation. And tuning a machine learning model is a dynamic process. So Bayesian optimization helps you to fine-tune the parameter, but fine-tune doesn't solve all the problem. Usually, if you find your model is not working very well, you should consider changing the network design instead of just using the BO to search for it. So the design and tuning is actually a reciprocal process. And that's why we need to actually do graduate student distance instead of just giving everything to the machine. Okay, great. So this is a summary of today's lecture. So we discussed about generative model, which contains a GAN and variational autoencoder. We discussed the semi-supervised learning with GAN. And we also discussed about representation learning technique, which is transfer learning and the contrastive self-supervised learning. And lastly, we talk about how we would like to search for hyperparameter of our machine learning model. And then I just bring up this point that tuning and design is a reciprocal process and they help each other. Okay, thank you. So this is the end of the practical machine learning course. Is there any questions?
I have a few questions, but I will ask, let anybody else have questions to ask first. Okay, so I got what you said about the optimization, but I lost how do you get the band to begin with from the correlation?
Oh,
so
the
how
band.
does yeah?
Okay, so 1 second. I need to reshare real quick. So the band, you can think of it as just randomly initialized. So it's a prior. So it is not very important. Like, well, I mean, it is important, but it's not very important. Like how wide each band is, and you do a few pre-runs. You can see, as I mentioned here. So basically, those black dots with no uncertainty, they are from the pre-run. So you just randomly sample from your parameter space, and you make a few points on your Bayesian, on your Gaussian process.
Okay, so then based on the distance, so to speak, between those dots, the algorithm will assign some band.
Yes,
Basically,
yes.
if the okay.
Yes, the
I
band
see.
is changing. Yes.
Okay. Another question is, if I may go back to the unsupervised learning.
Sure.
So it's again about this score between real and fake.
Yeah.
And yeah, so now that we established that it could be continuous, and even two cats can have some difference if they are, for example, a different color. Then I think that the feature map is probably the most important. I mean, the design of the filter is most important, right? Because you don't want your filter to focus on, for example, the empty space.
Well,
Right.
but remember the filter value changes during training, right? We cannot assign it any value to look at a certain task. But actually, the idea of machine learning is that during training, the empty space, for example, I mean, you will have empty space on both your car image and your cat image, right? So
Right.
in that case, it's going to automatically ignore the empty space. It's just going to try to
Right.
capture the shape, the color, the tone of the image.
Right, but for example, different filters with different size, I suppose one type of filters with different size can be focused on details such as the light of the car, and some bigger filters with bigger dimensions might be focused on for example, the size of the object. Is that correct?
Okay,
so,
that's not actually necessary. Okay, the good news is that I just have lecture 2 slide pull out, so we can discuss about this a little bit more. So do you remember the concept I discussed, which is called the reception field, Wenqing?
Kind of, that's the size of the size of the,
so the idea that
filter.
Well, in this case, I have the filter of the same size. The first layer, my filter is 2 by 2. On the second layer, my filter is also 2 by 2. But when you look at what this units correspond on the original image, it's actually already a 9 by 9, 3 by 3 image. So basically, by stacking more convolutional fields, a convolutional layer, your reception field is actually going to expand. So I think what you said is correct somehow, basically, but it's not actually about the filter side, but it's actually about the layers. It's actually about the depth of the layer. So for example, the lower layer, the reception field is low, so it can only probably capture some lower level information, like how a line is turning on your image. But as you go deeper and deeper, as you go to lower or higher layers of your convolutional neural network, your reception field actually increase, which allow you to aggregate all the features together into a larger awareness. So in that part of the neural network, you can capture like a higher level of feature, right? For example, yeah. For example, like what you mentioned, like is it a car? Is it a car? Is it a cat or something like that? Yeah.
Okay, thank you. That's okay. So the depth of the network is critical here. Thank you.
Yeah.
Then, so this slide here is using CNN as an example. Does this apply to other networks?
Oh, well, DeepInfoMax model is based on CNN, but I'm actually thinking about whether it's possible to apply it to like a recurrent neural network or even the multi-head self-attention model. Yeah.
Right, but in principle, unsupervised learning certainly applies to other networks for sure, right?
Yeah, yes, definitely, yes.
Okay. Thank you. That's all my questions.
Okay, great. Okay, if we have no more questions, I would like to thank you again for your attending. And I mean, all of you are stay through the last course, so you must be a true fan of machine learning. So I'm really glad of that. I will upload all my materials soon to the course website so that everyone could take another look. All right, thank you. Have a good weekend, and I will let me know if you have any question on any of the course material.
Okay, thank you again for the excellent lectures. We certainly have learned a lot.
Thank you, Obo. It was a very nice series of lectures.
Thanks.
It helped a lot.
All right, so I will talk to you later. See you.
See you. Bye.
Bye.